Yes, sir. How are you, sir?
I'm good. So in the last lecture, we saw parallel circuit also, right?
Yes, sir.
And mixed circuit also. So we are left with only one topic, but before that, let me give you some question to practice.
Okay, sir.
This is AC. AC. Okay. You have AC Verma?
Yes.
I think you just wait. AC Verma is not good. You have 43 years of JEE old question, PYQ, previous year questions.
Sir, I have a PDF of that.
Yeah, that's fine. Okay. Anyway, I have sent you one sheet actually. You can use it. So you can open the sheet now and let's come back to the bottom. Yeah. Come to exercise 2, page number 10. Okay. Yeah. So you can start solving from 1 to 9. Just for understanding. Not 9, except 9. All question except 9. 9 I will explain. You start solving it so that you can get the rhythm of solving question from here. Yeah.
Yes.
And then part 2 up to 6. That is sufficient.
While solving questions, sir, I find that while solving questions, I don't conceptually understand the difference between VRMS and V0. So, like mathematically, I understand it, but then I just
So
don't
these are
feel the
yeah.
difference.
So the thing is, you can think RMS as something called a mathematical definition, and which arises in many situations which led to its definition. So you can think this way. So let's say if you have some like system of particles, and every particle is having random direction of velocity. Okay.
Yes.
And the system is quite confined, so system as a whole is not moving. Central mass is at rest. So if you take the average of all velocity vector, what will happen? It will turns out to be zero. So because of the randomness, for every right there is a left, for every left there is a right, and because of the infinite number of particles, the symmetricity will give you zero answer. So the average is zero. Okay, in such a system. Now, to understand this RMS, no matter whether velocity is zero, average is zero, not, they have energy, right? So you can see everyone will have energy, correct? So
Yes.
what will be the average kinetic energy? So average kinetic energy you can write as half m. Let's say all are identical in mass. So you can write as v1 square plus v2 square, no matter what is the direction. Now this is something which is independent of direction, and it should be because we are talking about the energy, right?
Yes.
So the on an average, because every particle will have different energy. So on an average, what is the energy we are talking about? So we get something half m v1 square vr2 square and vn square by n. Now this term is you can say not convenient to write every time. So we thought of reducing it into something more meaningful and easier way of writing. So for that we define the RMS. So RMS is like you square the function, you take the average and then take the root. So if you square all velocity, if you take the average and if you take the root, this is called the RMS. So here, because velocity is the variable we can call RMS velocity. So the word RMS is a mathematical definition, and whatever you put next to it is the entity you want to convert into RMS. Understood?
Yes.
So let's say if we have a current which is varying like this, some random. So here, although it's a continuous function of current and time, but you can divide into small, intervals to make the analytical calculation. And you can call each term as I1, I2, and so on, I3, I4, and so on, so on. Okay. So when you try to calculate the average, it means some current will be positive, some will be negative, some will be positive again. So on an average, there is a cancellation also. But if you want to know the RMS value, because see, whether current is going right or left, the heat dissipated through the wire will be same. Okay. So let's say if you hit a person on the right cheek or left cheek, the pain will be in both cases, right? So
Yes.
for pain, you will go for RMS. You can think that way, but for the direction of motion of the person, you will go for average. Okay. So,
Yes.
so if you hit a punch from left side by 5 Newton, right from the 5 Newton, net force is zero, but it doesn't mean the net pain is zero. The pain is tremendous. In fact, it's doubled actually, isn't it?
Yes.
So RMS is something. It is mathematical for sure, but in many situations, in especially the statistical physics, it appears and it is a convenient way of writing. Also, what I have explained, when you talk about AC, so when you talk about AC, you talk about alternating source of voltage or alternating current source, current value. So in a circuit, it will move right or left. So let's say you talk about some random function which is not very much defined, some random function, but it is a continuous function. So I is varying with time. Let's call I is a function time. And if we have a resistor R, and if this I is moving through this R, so the power through the resistor at any instant will be I square R. And therefore the amount of heat dissipated in the time dt will be okay. Joule's law of heating. And therefore the total heat dissipation in interval will be integration of this function from 0 to time t. Now, because it is a variable function, so what is the average value? What is the constant value which we can assume, which will also lead to the same dissipation? So I want to know that constant DC current, if we assume is flowing constantly for a time t again, then the amount of heat dissipation is same. So in this case, it is I square R delta T. Why we are writing like this? Because here I is constant. Okay, so it's not variable. We need not to integrate, isn't it?
Yes, sir.
So if I equate these two terms, just the 2 and 1. So 1 equals to 2. I DC whole square R delta T. Ones are to be, let's call 0 to capital T, looks nice. And this I on the right is a variable I, it's not a constant. R is a constant, so we can take it out and it will get cancelled out. So this implies that I DC is I square dt upon delta T, which you can again write as dt. And this is square, so if you remove this, what will become root of this. Now, we are trying to find the DC equivalent of an of a variable current, which you can also think of sinusoidal current also. And by definition of RMS means root mean square. So you're squaring the function, you're taking the root, I mean mean of the function, you're taking the root. So this is by default IRMS. So basically you can say in alternating current or alternating voltage source, the RMS represents the DC equivalent of AC. Okay. So what is RMS representing? DC equivalent of AC. So RMS represents DC equivalent of AC. Okay. I hope the RMS meaning is clear. What is RMS?
Yes, sir.
So how many questions you solve?
Sir, last question, sir.
You can think like when you say RMS, you are replacing a DC circuit by some constant DC voltage RMS. Okay, think that way.
Okay, sir. Equivalent DC.
Yeah, it's equivalent DC. I have explained this in current and electricity chapter. Hopefully, maybe I have missed
Yes.
it. Yeah. So how many questions solved so far?
Sir, 8th question, sir.
Great. So what I'll do is I'll teach you the last topic, then you can solve the entire book easily. Okay.
Okay, sir.
So I would like to finish this chapter today only. And
Yes.
next lecture, I will start the modern physics. I think wave optics will be better, right?
Yes, sir.
Yeah, so I'll start with wave optics, interference, diffraction. Quickly we'll finish, and then we'll go to the modern physics. And after that, I'll come back to the portion of some 11. So heat and thermodynamics. So I'll take the heat and thermodynamics, conduction, and then we'll go to the, okay. So properties of matter is there. So these are small topics which we can be covered in every 1 to 2 lectures.
Oh,
Okay. So hopefully by January we should be able to finish everything.
yes. Sir, wave optics, how many lectures it will take, sir?
Wave optics will take a minimum of 3 to 4 lectures, including diffraction. Diffraction, including polarization, including polarization and diffraction both. Yeah, because these are three. Basically, these are 3 chapters, and we have actually interference. We have diffraction. Diffraction will have some instrument actually. So we have telescope, we have microscope, something like that, and then we have polarization as a theory, and then we have Brewster's law, which is very small part of it. So all will include only 1 lecture, and interference will take 2 lectures. Okay. And the base, okay, I'll give you some more historical idea that how it all started. So that will take 1 lecture. So that's why in total it will take 4 lectures of 3 hours minimum. Okay.
Yes, sir.
Yeah.
Yes.
Okay. So let's do the transformer. So we'll first put the definition. What is transformer? So it has to do something with that transfer, right? Because the word is trans. So transfer of something for sure. Or you can say transform something into something. So what exactly it does it? We need to define first. So let me give you the definition. It is a static device which transfers electrical energy from, sorry, which transfers energy from one electrical circuit to another electrical circuit with the help of magnetic circuit. It works on the principle of mutual induction. So this is the definition. Okay. So you will hardly find definition in books. They don't define the meaning of transformer. They simply say transformer, and they start with some equation, but there is a definition. So the purpose of transformer was very simple. So generally, when we go to power plants where we produce electricity, and what is the meaning of produce electricity means? Using the Faraday's law, you have some sort of turbine which is connected with a large tons of wire called the loop, and it is generally mounted on a armature which is made of iron actually. And why it is mounted on iron? Because of the obvious reason, iron is having the highest permeability, and because the size of the armature is really huge, so it is very difficult to turn that loop using human force. So we are not capable of turning effectively. So we need some source to turn it. Okay. So now there are many ways to turn that armature, because eventually that armature will connect with a dynamo, and dynamo will have the wings actually. Okay, very strong wings, non-breakable, very strong, and not just strong, it's very large in size also. So what generally we do is uh, we can do it by heating the water, boiling the water, creating the steam under very high pressure, because at a very high pressure what happens, the steam will have high density, and these steams are sent through the chamber in which dynamo is present, and when the steam will hit the dynamo wings, it will create a thrust, and because of the tremendous amount of steam being you know forced into that chamber, the turbine will start rotating, and as the turbine will set into motion, because of the high mass, the inertia is really high. So once you set this into motion, the effect, the intensity required to continue is not very much. So a slightly small thrust of steam will keep on rotating, and as it will rotate, the flux will change, and as the flux will change, what will happen? As the flux will change, EMF will be induced,
Yes.
and those EMF induced is used to store large batteries. So eventually we store the charge, which is called storing the energy, because every capacitor will have charge and energy at the same time, right?
Yes.
So we have electrodes. So indirectly, these are capacitors, which stores charge, and the storage of charge is the main function of battery. And this energy is not transmitted using uh, the wire cables from the power plant to the cities, villages, industries, and while reaching the city, it is sent to a small power grid. Power grid is basically a distribution center you can think of. So once they receive that power, there is a continuous flow of power. So it is not there is no breakage of power. It keeps on coming, and you need to keep on consuming. There is an issue that if the rate of production of energy is more than the consumption, the thing is it's difficult to manage actually. Okay, because there is no container to store tremendous energy. So luckily, we are as a city we keep on consuming. Imagine if the entire city is shut down, every switch is shut down at the same time for the entire city. Then power grid will be under tremendous pressure. It may break down. It may undergo some issue also. So that has happened once. But anyway, the whole idea is you receive energy continuously from the power plant to the grid, and grid will lower the voltage, because for operation of the household devices we need just 220 volt. So 220 volt is the RMS power, RMS voltage supply in most of the Asian countries. In US, the RMS voltage supply is simply 110 volt. So the difference is they have higher frequency compared to us. So in India, the operation is happening at 50 hertz of frequency, as I discussed in the beginning. But in US, the frequency uses 60 hertz. So some of the Western country uses 60 hertz, and most of the Asian country uses 50 hertz. And the RMS voltage that we use for the household supply is 220, and they have 110. So we have some sort of inbuilt transformer in most of the devices which can deal with the because the world has globalized, so people are going from one place to other place, and if the device which they carry with themselves will not work in the other country, it is really a big inconvenience for both of them. So people coming from there to India, or we going from here to other country will face the problem. So there is a inbuilt transformer nowadays in most of the devices which can deal with both kind of voltages. Or we have something called adapter. So the word adapter has come from the same thing. It can adapt to the different protocols being followed in different parts of world actually. So So that's why, okay, nowadays devices are like, manufactured with the aim of global consumption, and therefore they design the adapter which can work in all voltages. So transformer is basically a device. So we need some source of energy. So power plant is the producer of electrical energy you can think of, and to transfer we need transformer. Okay, so we need actually wire, but there are some issues if we transfer without doing some modification. So we'll come to that very soon. Now, to design a transformer, it's very simple. You simply design any shape of iron core. Okay, so we'll keep it pretty much simple. Let me show you. So this is going to be my iron core. It's a two-dimensional view. It is actually three-dimensional. Okay, so move on.
Yes.
So this is the iron core. It's basically like this. Okay, so you can think as a big cube, and a part of a cube is removed. So it's a hollow cube. Okay. Now this is called the iron core. Now iron core is not supposed to be only of this shape. You can design iron core of any shape as you wish. So you may think of designing the iron core. You may take a simple iron rod itself. So if you take only iron rod, okay, it could also behave as transformer. You can also take, if you want, you can take a circular one. So the shape really doesn't matter. Now, what you're supposed to do is you're supposed to, wrap a large number of turns of wire onto this core. Now, the large number of turns of wire which you have wrapped, if connected to the actual source of energy, then such coil is called the primary coil. So primary coil is that coil which is connected to the actual source of energy. So generally at a power plant, we have the actual source of energy. So that is called the primary coil. But for every transformer, the way energy is transferred. So if this energy is going to someone else, and if this is the receiver of energy, and there is other part which is consumer of energy. So consumer is called secondary, and the receiver of energy is called primary. So there are many ways of saying primary coil. So this is your primary coil. So this is the primary coil, EP, and EP is called the EMF induced, and at the end of primary coil. And this is actually the energy giver. So primary is always connected to source of energy. So somehow primary also dictates that how much energy we are going to eventually supply to the other coil. Now, In the same core, wherever you want, you can wrap a large number of turns of wire here, here, or maybe like this, doesn't matter. What really matters is you must wrap some turns of wire here also. For the circuit diagram representation and all, we choose to represent on the opposite side. And this may be the connection or the terminal which is connected to some sorts of appliances or any consumable device. So we call this as the load. So you connect with some load resistance. Load means any appliance, okay, or maybe household or whatever, you can name it. So this is the consumer part. This is your load resistance. And the potential which obtains across this end is called secondary. And the number of turns of the primary coil which we decide is called NP, and the number of turns of secondary which we can again decide is called NS. And the ratio of secondary upon primary is called turns ratio. The same thing, if you choose to, implement in other shape, you can do the same way. So if we keep just one primary and only one secondary, the mathematical analysis will be easy. And why we put on the other side, the reason is we want to, minimize the direct interaction of the two coils. That is one of the reason. So we want the interaction to take place only through the medium, which is this iron core.
Yes.
You can do the same thing here. Again, we have primary here, and you can wrap somewhere here, and you can call secondary if you connect a load, something like this. So this is. So all are just diagrammatic representation. You can choose whatever you want. I'll choose the middle one because that's very famous, used in books. But you can see everything. I mean, all types of configuration. Now, number of secondary source, you can take more than one also. You can wrap more turns in some other place, and you can also call that secondary source. Generally, it is not recommended, but if you have multiple sources as a secondary source, okay, in a single iron core, then again, the description, the mathematical explanation will become more and more complex because all three can interact. Okay. So the mutual induction will become a more rigorous one, and such circuit it will be difficult for us to analyze. So what we are going to assume in our case for the JEE that there is no direct interaction of the coil. So there are a lot of assumptions that we make before we do the mathematical analysis of ideal transformer. Okay, let me draw this transformer once again. Okay, so we have this circuit. So first of all, what will happen? We know that the moment the IP is established, the moment you create the IP, okay, every current carrying coil will create the magnetic flux, right? And once you create the flux, what will happen? The flux will. So if you remember the ideal solenoid, the flux was like this,
Yes.
and it will just enter, exit the solenoid, will get diverging, like this. Now, if I remove the air, if I create a path like this, which is iron core, so the same lines of force will turn here actually, and they will try to move through this path. So giving a magnetic path is like giving you the flyover. So instead of going there and coming back from infinity here, they will not do the same thing. What they will do rather is they will do the circulation in the medium itself. So the lines of force which is produced will travel and come back, but in the medium itself. Do you realize what I'm saying?
Yes, sir.
So what you establish is called circulation of field, or you can say there is a flux circulation, and this iron core is making it feasible for flux to circulate within this medium, because iron is a ferromagnetic substance with very high permeability, and therefore electric field lines, okay, sorry, magnetic field lines will prefer to go through this medium instead of going through the air. Don't take this diagram strictly. I mean, this is just a matter of convenience of drawing. It may be a smooth turn, okay, not a sharp turn.
Yes.
Now, again, we cannot guarantee that all lines of force, and or you can say 100% all lines of force will move through this path. Sometimes there is some leakage of lines of force. Some lines of force may go through air also. Okay. Now that is a small part of it which is going to go through the air, and such situation is called flux leakage. Okay. So in a real transformer, we have something called flux leakage. Okay. But when we talk about the ideal transformer, that is our syllabus. We believe that there is no flux leakage. So whatever flux primary will produce, the same number of lines of force secondary will receive. A flux loss means that the lines of force received by secondary will be less than lines of force received by the primary, which also means the rate of change of flux in the primary is more than the rate of change of flux in the secondary, which also means the EMF induced in the secondary will be less than EMF induced in the primary for a single turn, for each turn, you can say. Okay.
Yes.
But when we talk about the ideal transformer, we never talk about the flux loss. Okay.
Yes.
Okay. Now, when you create a magnetic field, iron is a substance in which we have something called domains, which is similar to the dipoles in case of a dielectric, and domains will behave is similar to the dielectric dipoles. So when you apply a magnetic field, the domains of the iron core will try to align itself along the field. Okay. In the process of alignment, even if you remove it, they will not become random to the same extent as they were. Rather, the removal of field will left the medium with some magnetism intact. So you might have experienced that if you rub a coin for a long time with a magnet, the coin also becomes a bit magnet, right? And
Yes.
also acquires some attractive power, although it is not a magnet. So this property of a medium to retain the magnetism even after removal of the field is called retentivity. It's called retentivity. And to remove that retentivity, to make it again back to zero, if you want to demagnetize, because the coin has become magnetized. So to again make it demagnetize, what we do is called, we apply a reverse field, and that reverse field eventually make the entire magnetism back to zero. So how powerful a reverse field which we need in order to make the retained field to back to zero is called coercivity. So there are two terms which you will come to know. One is called retentivity and coercivity. How to spell coercivity? Coercivity. Is this the spelling? Coercivity?
Yes. Um,
You can
sir,
check
I
actually.
think COERCIVIT, right?
COER. Okay, COERCI. This one?
Yes.
Okay, if it is wrong, you can rectify, you can correct it. So we have two properties of a medium called retentivity and coercivity. And generally, it is desirable for transformer to have very less retentivity and very less coercivity. The reason is, in transformer, we are going to apply the sinusoidal source of primary source is sinusoidal, so it will keep on altering the direction of current, right? So current will be up and down, up and down. And we want a similar fluctuation for the secondary also. But the thing is, even if you switch, the core will not go back to the same value very effectively. So this kind of, there is a loss actually. So every time you need to first retain, you will retain something, then I will coerce to make it zero. And this entire process of magnetization and demagnetization of a iron core lead to loss of energy. And this kind of loss of energy is called hysteresis loss. So you can say magnetic hysteresis loss.
Oh,
Again, hysteresis, okay. So in the, if you have read the book S.C. Verma, Magnetic Properties of Material, you might have seen a leaf-like diagram. A leaf-like diagram between the I versus H, and the diagram goes like this. So this is called hysteresis, whatever, loop. The arrow is the direction of changes, and the area under the loop will give you the loss of energy per unit volume. So it's called the energy density actually of loss. So how much energy is lost per unit volume of the medium? So the area of loop will give you energy loss per unit volume of medium. Okay. Now in real transformer, sorry, in ideal transformer, what we assume? No loss. So there is no such loss which we assume. Now, because you're wrapping a large number of turns of wire, so that wire will also offer you some resistance, correct? And
Yes.
therefore, some heat should be produced in the coil itself. So such loss is called copper loss. For historical reason, earlier the wire was only made of copper. Now we have aluminum also, copper also, something else also. But anyway, the name is for historical reason. We call it copper loss, or it is called I square R loss. Okay. It is simply the resistance of the loop itself will create this loss. And in ideal, again, we assume no copper loss. Okay. And the last loss, kind of loss which you need to know is called, I don't have space, but I'll continue here. So it is called AD current loss. So as I said, here we have the iron core, and if iron core will have some surface area because it's iron, so it's a metal with the surface area. And if a surface of a metal is, is brought into a time varying magnetic field, then the surface will induce some current. So some current will, start flowing in the surface itself. And that current will also lead to the some heat loss. So that loss is called the eddy current loss, and that can be minimized by reducing the area. And that is why an iron core is designed by taking a thin sheet of iron and sticking them together to create this entire shape. So you can think as a coaster. You take a multiple coaster, you put one over that, you make a stack of it, and every coaster is kind of isolated with each other. So it will never let the current to create, move over the surface. You break the surface with some electrical insulation. So that can be minimized to a greater extent. So these are the losses that you need to know between the real and ideal transformer. Okay.
Yes.
So now, because we are going to study about the ideal, so we are neither going to consider the flux loss or any hysteresis loss or any copper loss or any AD current loss. Okay.
Yes.
So we are not going to talk about any kind of loss here. Okay. So for ideal transformer, under the zero flux condition, we can say flux in the primary, the total flux first is total flux you can say flux per unit term remains same in both coils. See, by creating more number of turns, you will have more flux, right? Because flux is count of lines of force through each turn, right?
Yes.
So if I have, let's say 10 tons, then I have something into 10 times. If I have 20 tons, then I have something into 20 times. So flux definitely depends on how many wrap and how many turns you wrap around the iron core. But the flux count for one ton will be same for both, because we are assuming there is no link, there is no loss of flux, there is no flux leakage. So we call that the total flux in primary per unit turn is same for both.
Yes.
In a real world, it could be flux per turn in primary is some factor, or you can say opposite wise. If there is a loss of flux, then we can say the flux per turn in secondary is some fraction of flux per turn in primary. So there will be some relationship. So for real transformer, the base equation will change like this. Eta will come as a fraction. So maybe if 10% is lost, then eta becomes 0.9, correct? If the 10% of flux is lost while going from here to there, so secondary will receive 10% less, which is it will receive only 90% of the what primary is receiving or producing actually. Understood?
Yes.
So now we can differentiate both sides and we can put a minus sign. So 1 by NP into d phi b by dt. So basically we are going to use the Faraday's law. So the rate of change of flux in the primary coil is called the primary EMF, or you can say EP, and NP will come as a bonus. ES by NS from Faraday's law. Okay, so therefore the secondary EMF under no loss condition. In case of real, we don't write E, we write V actually, because you don't get EMF, you get the potential difference, because there is some resistance to the wire itself. So things will be real, slightly different from things in ideal case. So we write E secondary equals to N secondary upon N primary into E primary. So NS by NP is called the turn ratio. So you can see that the secondary EMF may be more than or less than or equals to primary EMF. So E secondary is so if I take case one, if NS is more than NP, if you have more turns wrapped in the secondary coil compared to the primary coil, in that case, what will happen? The ES becomes more than EP, and this is called the such transformer is called what we call is step up transformer. Okay.
Yes.
So if you want to increase the voltage, let's say if you purchase some device in US and you come to India where the voltage is 220, so you need to step up transformer, right?
Yes.
And now if the secondary having less turn compared to primary, then definitely secondary will also have less than primary EMF, and we call what we call step down transformer, right?
Yes.
And the last scenario, if NS equals to NP, so if NS equals to NP, then ES equals to EP, then what is the purpose of such transformer? But before that, what could be the name? It is called 1:1 transformer.
So then what's the point?
Yeah, that's interesting. So transformer, the way transformer is designed, it gives isolation to two separate electrical circuit. So let's say you want to drive a large number of similar components of electrical circuit. So as a manufacturer, let's say if you need 1,000 of same similar components, so manufacturer will do the manufacturing of one component and it will make the replica. You can say it will create or manufacture same component again and again. And if you want to couple all such component together, you can use transformer to drive each component. And because you want everyone to receive the same power, so you will use the 1:1 transformer. The benefit is it will prevent from damage. So if one gets damaged, other component will be still working fine, right?
Yes.
So you need not to change the entire, you can say entire component together. Rather, you can just replace one of the unit and you can get it working again. Okay. In fact, large repetitive circuits are designed in component. So you just look at the repetitive model and then you connect, or you can say you couple it using the transformer. So you can also see transformer, attached in many electrical devices if you have seen something. Okay, anyway, so it's called buffer transformer. You can say think as a buffer. Okay. Now, what is interesting that a high voltage will make sure that you will get high current, yes or no?
Yes.
And ironically, the answer is no. High voltage doesn't mean high current. You know why? Because that is called the violation of conservation of energy. If primary is giving you 100 joule per second, can you produce more than 100 joule in secondary?
No, sir.
Because secondary is receiving energy from where? Primary only, no?
Yes, sir.
So secondary cannot consume or use energy more than given. In reality, it only consumes a very small fraction of what primary is able to produce, 50 to 60%, 70% maximum. But in ideal transformer, we assume there is no loss. So our assumption that the loss is nothing. Always remember the EMF depends on the flux concept, but current in a circuit depends on the energy concept. Okay. So we
Yes.
talk about the power transfer. So there's something called power transfer. So what we need to remember that voltage depends on flux transfer, but current depends on power transfer. Okay. So, okay, I'll write it. Current in current in primary and secondary coil depends on current in primary and secondary coil depends on power transfer. Okay. But voltage depends on flux transfer, right?
Yes, sir.
So power we write as V into I, or you can say now E into I in ideal case. And that is why the EP into IP, which is the power generated in the, so the plant is giving you P power. So the current and voltage relation in the primary coil is going to be this one. Understood?
Yes.
And under zero loss condition, we can say that the secondary is going to receive the same. Under
Yes.
zero loss condition. If there is a loss, then a fraction of this will be received by secondary. Okay.
Yes.
So under zero power loss. 0. Okay. So unless, see, if I say there is no flux loss, but if I say there is a power loss, then EMF relation will not be affected, but the current relation will be affected. Understood?
Yes, sir.
But it never happens. The thing is, like, if there's a flux loss, there is definitely energy loss. I mean, energy and flux are related. But even if I say hypothetically assume that there is no flux loss, but there is energy loss, then yeah, I mean, of course, the energy loss could be due to the copper loss, AD current loss. So energy loss can be due to various other reasons. That's why it is possible even in practical scenario that there is no flux loss, but there is still some power loss. Okay. And this leads to the relation that the secondary current in upon primary current is EP by ES. And we know that EP by ES will follow which formula?
P by NS, the number of turns.
It is.
Sir, NP by NS.
So you can see clearly the IS turns out to be NP by NS into IP, which is the inverse relation, right?
Yes, sir.
So as you become greedy by increasing the voltage, the current will become less. So making too many turns will make it useless, because if you attach a fan and if fan is not getting any current, what is the purpose of fan? Understood?
Yes.
So what is very interesting that even high voltage will not show that, okay, make sure that, okay, you will get more energy, more current. High voltage and current together depends on the source. So the power is something that we need to look for, not the individual term. Understood?
Yes, sir.
Okay. So IS is, it is an inverse ratio. So if you try to increase more turns in the secondary, definitely you can get high voltage, but any device which you connect to the secondary will receive almost no current, which means it is not at all going to work. So you have to restrict your greediness. Okay. So no one can be greedy. The God has designed in such a way. You have to conserve the energy, right?
Yes, sir.
But there is a benefit. The benefit is still, if see, if there is a very high voltage, there is a very less current, then what is the benefit of very less current? So benefit is the transmission. So you might have seen while traveling in train or bus that in the side of the in the fields, you must have seen something like this shape of a structure with cables running like this. Have you seen?
Sir, I haven't traveled.
Okay. So just a moment, I'll show you. So this is simple transmission lines. This is called transmission lines, and see how to supply the energy from the power plant to the city, which is maybe 1,000 kilometers away. How it is possible? So you need some
Oh,
physical
sir.
source.
Yeah.
Yeah,
Sir, are you talking about the towers?
yeah, towers. Yeah,
Yes, sir. Yes, sir, I've seen this.
towers with wire cable.
Yes, sir.
So these cables carry energy. Okay, but the problem is this cable will have some resistance. So if it will carry I current, then the power loss will be I square R. So
Yes, sir.
if I'm sending, let's say, 100 joule per second at this point, and if there is a loss, so the next tower will receive less value,
Yes, sir.
which is not good, right?
Yes, sir.
So we want that power should reach the other source, city or whatever location without much loss. The loss should be almost negligible. And for that, I need to make I as small as possible. So there we use a step up transformer. What we use? So to minimize the copper loss in the cable, although cable will have less resistance, but still there will be some loss because it is kilometers long, so it will have a significant loss while traveling. So this copper loss we can minimize. So that's why the generic way of transfer of power from the manufacturer to the consumer takes place in this format. So I'll draw something. Let's say we have a power plant. Let me draw something like this. And then there is a city skyline. So now this is the city. This is the power plant. So before the transmission is done, we use the step up transformer. So the cable will reach here, the power, the voltage will increase many times. So we increase the voltage by tens of thousand times. Just a minute. Okay. So the first step is near the power plant, you step up the transformer in the voltage. So whatever voltage you're producing, you step up to. So here we have the that the coil turning and all, right? And we have seen that the maximum value that you can produce by turning coil is NBA omega, if you remember. And so the
Yes.
RMS you can produce is E max by root 2 by definition of RMS. And now this will pass through the large distance, crossing rivers and the fields and country yards, whatever you can call it. And then when you come near the city, before, so it is generally put in the power grid. So this is like power grid. So the moment it comes to power grid, what they do? They step down the voltage for city use. So power grid will use the step down transformer. So if the power produced here is P1, and if you think there is a loss, if loss is very small, we can ignore it. But if it is significant, we have to consider. If the loss of power is delta P, then the power of the secondary will be P1 minus delta P. Okay. So power will decide the product of ES into IS. Okay. And this P1 will decide the EP into I. Understood?
Yes, sir.
So if you remember this diagram, you can solve any question. Okay.
Yes.
So this is the end of this entire relationship. There is one more thing that You can ignore because that is not part of JEE or any other part. So it is called the impedance relation, but I think we should avoid it as of now. So now with this, you can solve any question of AC. I have given you a sheet. Try to solve question. If you get stuck or if you have doubt, I'll clarify once again. Okay.
Yes.
And I'll try to give you more questions for practice from AC. The better way is solve this sheet and solve the previous year AC question. That is more than sufficient. So it's not a very big topic. It will carry one question max. And it is always related to the EMI chapter. So if you know EMI really well, and if you know the functioning of transformer, you can solve this easily. So this diagram was important to you, that how we use the step up and step down, and how the power relation we write. And as I said, the voltage relation doesn't need power equation. Voltage relation depends on the flux relation. Okay.
Yes.
So in a transformer, if the flux on this side and flux on this side is changing, then there is a voltage. So voltage on this side will be different from this side. If it is same, then same voltage. Different, then different voltage. So voltage relation depends on the flux relation. Okay. So if you keep only these two concepts in mind, that's more than sufficient. Any loss of energy will affect the secondary. So primary will produce, we see primary is consumer receiver of energy. So it will receive whatever, but secondary will get as per the loss also. So when you try to write the relation of power between primary and secondary, you have to compensate for the loss. Okay.
Yes.
So if question says that there is some loss, subtract the loss, then write the power relation of secondary. Okay.
Yes.
So the EP, the ES will follow only this relation, NS by NP into EP. So for this, we do not need power relation. Okay. And we are believing there is no flux leakage loss, no flux leakage. So if there is no flux leakage, this is equation you can always go with without any hesitation. But current relation depends on power, so you have to think of power first. Okay, so this is the relation I have written here. Or if you have loss, in fact, if you have loss from here to here, the current even here will change accordingly. Okay. So keep these things in mind, and hopefully you will not face any difficulty in solving question of transformer. Okay.
Yes.
So with this, we complete our alternating current.